Well, let's take this idea, and again, this will be in broad strokes. When we think about the R groups, we want to divide the R groups into some pretty broad categories. So that if we start with the nitrogen, and we put an R group out here, this R group can be 20 different moieties. Now, in some cases, this R group may only be a hydrogen, and that's a glycine. Sometimes it will be 2 carbons. But the idea here is that we have R groups, and we're going to generalize these R groups into those which are uncharged, i.e. hydrophobic. Other of the R groups these R groups will be charged. Examples of these are glutamate and aspartate. Along with glutamine and asparagine, I think. But the third one out here will be uncharged. This will be, the third one out here will be polar. And these are molecules such as serine and threonine with hydroxyls, and also methionine with a sulfur. Now again, a biochemistry course where you're going to drill down and find out all about the details of this. All I want you to be able to do is recognize that we have amino acids with these generalizable characteristics determined by the R groups of uncharged, charged, and polar. Charged and polar. Whenever you see this term charged or polar, these guys are hydrophilic. And this one, the uncharged, is hydrophobic. This brings us round again to the glib statement of lowest thermodynamic state, the most probable state. So the next idea is how you use these R groups and orient these R groups either with respect to the water or away from the water. And that orientation of the R group now begins to generate the three-dimensional shape of the protein. So here what we're going to do on the second part of the panel is we're going to describe the idea of R groups. And their interaction with water largely determines the three-dimensional, you can read tertiary, structure of the protein. Now I'm going to simplify this, and I'm going to draw up here a kind of squiggle, and we're going to start with the amino terminus because we need an endedness. We have this protein which is in water. Now again, I've drawn this in 2 dimensions and recognize that this will actually be in a 3-dimensional structure. And that each one of these amino acids will have an R group. Now, some of these R groups will be uncharged. Let me make this as an R. The green R groups are uncharged. We can do it this way. Let me not do it this way. I can see where this is going to be confusing. So these R groups here are uncharged. And the ones in blue are meant to be polar or charged. Now, although I've laid them out here on a string, what I'm trying to convey is that these uncharged R groups are not going to interact readily with water. So the lowest thermodynamic state for these R groups is to hide from the water, turn inward. And these R groups will form a hydrophobic region. Of the protein. Meanwhile, the blue polar charged groups are going to turn out. They're going to face the water. So in regions where the protein is facing the water, the polar or charged R groups will be facing the water. In regions of the protein where we have hydrophobic amino acids, hydrophobic amino acid charged R groups, those then will be turned inward. So now we begin to see how we're going to generate a 3-dimensional shape of the protein. And the 3-dimensional shape of the protein is going to be a combination of the R groups which are facing the water and the R groups that are hiding from the water. And that's the first level of 3-dimensional structure that we get from this. We can then have regions within the protein here where we'll have charge interactions, and we can see this is a binding pocket. Well, let's stop this here, and I'll bring us back tomorrow with a slide that will show us how this 3-dimensional shape forms.